welcome to the 13th lecture of the course. So, in the last lecture we showed that the following language 0 to the power n, 1 to the power n, where n is greater than or equal to 0, is not regular using the pumping lemma. So, what we plan to do today is look at some more examples of non-regular languages and then give a proof of the pumping lemma. Why is the pumping lemma correct? Okay. So, the next example that we will see is the language L2, let us call it L2. Okay. So, let us take a language over the alphabet ABC. Okay. So, we will look at all strings of the form a to the power L, b to the power m and c to the power n, such that let us say L plus m is less than or equal to n. Okay. So, let us say that L, m, n are non-negative integers and L plus m, that is the number of b's plus the number of a's, is at most the number of c's. So, the claim is that this is also a non-regular language, and let us try to prove this using pumping lemma. So, once again in the as we saw last time, so we will treat the pumping lemma. So, we will look at the contrapositive form of the pumping lemma and we will treat it as a game between you and an opponent. Okay. So, in the first step your opponent gives you a number. So, given p, so this is your opponent's move. So, you choose a string w that belongs to the language which has length more than p. Okay. So, what string do we choose that belongs to the language? So, in this case what I will choose is, I will choose the string w a to the power p, b to the power p and c to the power 2p. Okay. Now, let us verify. Clearly this string has length more than L, and if you look at the number of a's plus the number of b's, it is equal to the number of c's. Okay. So, hence it belongs to the language L2. Okay. So, this is your move. So, if it is your opponent's move, it is given to you, you do not have any control. If it is your move, you can choose any string that you want that satisfies the constraint. So, now again your opponent will make a move. What move does your opponent make? So, your opponent partitions the string into 3 strings x, y, z, such that x, y has length at most p and y has length greater than 0. So, if x, y has length at most p, what can the strings x and y contain? Okay. So, observe that the way we chose our string w, if x, y consist if x, y has length at most p, then it consists only of a's. Okay. It cannot have a b or a c because the number of a's is p. Okay. So, given a partition w equal to x, y, z such that x, y is at most p and y is greater than 0, we have in particular the string y consists only of a's. So, y is equal to some a raised to the power t for some t strictly greater than 0, okay, because the length of y is greater than 0, and it consists only of a's because of what I just said, that the length of x and y is at most p. Okay. So, this is again your opponent's move. So, now what I do you choose? Okay. So, now you have to choose an I such that x y to the power I z does not belong to the language. Okay. So, in this case we will choose I equals 2. So, let us see what happens if we choose I equals 2. So, if we consider the string x y square z, how does it look like? So, x y square z is basically nothing but I have x y, I mean basically it has an extra y in between. Okay. So, it has an extra number of it has t extra number of a's. Okay. So, basically the string will be a to the power p plus t. Okay. The number of b's and c's are the same, b to the power p, c to the power 2p. Okay. So, this implies that number of a's plus the number of b's, okay, is strictly greater than the number of c's, which implies that x y square z is not in the language. Okay. So, this happened because we have t that is strictly greater than 0. So, now in this case we chose I equal to 2, but what would have happened if we chose I equal to 0? Okay. So, observe that if we chose I equal to 0 here, then x y to the power 0 z would have been the string a to the power p minus t, okay, because it does not have that many number of a's, b to the power p, c to the power 2p. So, number of a's plus the number of b's would be p minus t plus p, which is less than 2p, which is less than the number of c's, which would not have put the string x y to the power 0 outside L2, and that would not have worked. Okay. So, basically what I am trying to say is that I equal to 2 works, but I equal to 0 does not work in this case. Okay. So, this is one difference between what we chose I this time and what we had for our language L1 last time. Okay. So, and this proves that L2 is not regular. Okay. So, now let us look at another example, our next example. Let us look at the language L3, which consists of strings in 0 1 stars, okay, such that the number of zeros in W is equal to the number of ones in W. Okay. So, it has equal number of zeros and ones, but the crucial, I mean the difference between this and L1 is that in L1 all the zeros were contiguous and all the ones were contiguous. So, we had a sequence of zeros followed by a sequence of ones. Here that is not the case. Here we have, they can be distributed anywhere. For example, 0 1 0 1 belongs to the language L3. Okay. So, how do we prove that L3 is not regular? So, actually here instead of using the pumping lemma, what we will do is we will use closure properties. Okay. We will use closure properties of regular languages and show that L3 cannot be regular. So, first consider the language of the regular expression 0 star 1 star. Okay. So, 0 star 1 star is a regular expression that corresponds to the language where we have a sequence of zeros followed by a sequence of ones, and they can be any number of zeros and any number of ones. Okay. It is not necessary that the number of zeros are equal to the number of ones. Okay. So, and you can very easily construct a automaton for this language also if you want. But anyway, so we consider the language of this regular expression L of 0 star 1 star, and we take its intersection with our language L3, that is strings which have an equal number of zeros and ones. What is the answer? I mean, what language do we get on the right hand side? So, if we take all strings which have a block of zeros followed by a block of ones, and it has equal number of zeros and equal number of ones, it is nothing but our old language 0 to the power n 1 to the power n. Okay. Equal number of zeros and equal number of ones in a contiguous setting. Okay. So, this is nothing but the language L1. Okay. So, we know that this guy is regular, okay, because we have a regular expression for it. If L3 is regular, what does that imply? Okay, so, if L3 is regular, then by the closure property of intersection, so regular languages are closed under intersection. So, this guy is regular, this guy is regular. So, intersection of these two would also be regular, but that is not the case. So, if L3 is regular, then it implies that L1 is regular, but we have already seen earlier that L1 is not regular. So, this is a contradiction. Okay. So, this is a contradiction, which means that L3 is also not regular. Okay. So, here I want to make a point. So, here to prove that a language is not regular, what we are using is that we are taking another regular language. We are looking at the operation between our given language, our candidate language, and this regular language, and we are showing that there is some other non-regular language. So, this guy is, we know, is not regular, and this allows us to prove that L3 is not regular. Okay. But here a common mistake that beginners tend to make is that is the following, that so suppose instead of this, if we had something like let us say some, let us call it L, some language L intersection with some language L prime gives, let us say, an language L double prime. Okay. So, if L is regular and L prime is not regular, okay, it does not imply that L double prime is not regular. Okay. So, this is a fallacious argument. Okay. So, this is not correct. So, if we want to show, if we have a language which is regular and we take another language which is not regular, their intersection might very well be regular also. Okay. Even more, okay, if L and L prime are not regular, even then L double prime may be regular. Okay. Even if you have two non-regular languages, you can take their intersection and get a language which is very well regular. Okay. I mean, a simple example here is, for example, if you take the language, if you take any non-regular language as L and you take the complement of that language as L prime. Okay. So, if a language is non-regular, its complement is also not regular because of this same because of this reason, and the intersection between a language and its complement is always an empty set, which is a regular language. Hence, we get a regular language by taking intersection of two non-regular languages. Okay. So, this is a key point which should be kept in mind. Okay. So, now let us look at our last example of a non-regular language today. So, we have a unary language this time, a language which is over a single alphabet. So, it consists of all strings of the form 0 to the power p, where p is a prime. Okay. So, what is a prime number? A prime number is a number which is divisible only by itself and 1. So, how do we prove that this is not regular? So, once again, given in this case, let us say given, well, I cannot use p, so let me use another symbol. So, given q greater than or equal to 0, choose w equal to 0 to the power r, where r is a prime greater than or equal to q. Okay. So, pick any prime number that is more than greater than or equal to q as this. So, by definition w belongs to the language and it has length at least q. Now, given a partition of w as x, y, z, where let us say that the length of y is some t, okay, we will choose. So, what do we choose I as? Okay. So, we want to choose I in such a manner, so that x y to the power I z, the length of x y to the power I z will not be a prime. Okay. So, that is what we want to choose I as. So, let us take in this case I as r plus 1. Okay. So, we choose I equal to r plus 1, where r was the length of w, okay, it was the initial length of the string. So, what do we get? So, then x y to the power I z is nothing but, so what is x y to the power I z? So, I can write this as, so I have 0 to the power r over here. So, x y z is my string w, which is 0 to the power r, and then I have another I minus 1 many y's. Okay. So, this will be 0 to the power r plus I minus 1, which is r plus 1 minus 1. So, let me write this as I minus 1 times that many y's. So, I minus 1 times t. Okay. So, what is this number? So, if I just write this down, so this is r plus, so I minus 1 is nothing but r plus 1 minus 1, which is r t. So, this is equal to r times 1 plus t. And now, what are r and 1 plus t? So, r is the r is a prime number that has length more than q, which means that r has length at least 2. Okay, 2 is the first prime, and t has length t has value that is at least equal to 1, because t is the length of y, which is strictly greater than 0, which means it is at least 1, which means that 1 plus t is at least 2. Okay. So, what we get is a composite number. Okay. So, this is not a prime, okay, which implies that x y to the power I z is not in L4. Okay. So, that completes the example. So, now as I said, we will give a proof of the pumping lemma, and that is going to be the last thing we will discuss today. So, recall the statement of the pumping lemma. Let me write it down. So, the pumping lemma stated that if L is regular, then there exists a number p greater than or equal to 0, such that for all w belonging to L of length at least p, there exists a partition w equals x y z, where x y is less than or equal to p and y is greater than 0, such that for all I greater than or equal to 0, x y to the power I z belongs to L. Okay. So, let us prove this lemma. So, if L is a regular language, what can we say about L? So, if L is a regular language, then basically we, by definition, there exists a DFA for L. Okay. So, let, this is our proof, let D equal to Q sigma delta Q naught F be a DFA for L. Okay. So, now what can we say about the DFA? So, let us try to understand. So, first we need to we need to show that there exists P. Okay. So, if L is regular, there exists P. So, we set P as the number of states in the DFA. Okay. So, in this DFA, we will set P to be the number of states. Now, if we, so let us look at it in a pictorial manner first. So, let us say that this is my DFA So, here is my start state q naught. So, if I take a string w, okay, that has that belongs to the language L, which means that it is accepted by the DFA, and it has length greater than or equal to p, what does it mean? Okay. So, what it means is that there is a path from, or not path, there is a walk from uh, the state q0 to some accept state of the DFA on given the language on given the string w. Okay. So, this is my DFA D. Okay. So, there exists a path or there exists a walk which starts at q0 and it ends at an accept state of the DFA. Okay. So, given w in L such that length of w is greater than or equal to p, there exists a sequence of states q0, q1 up to q let us say t, okay, such that t is greater than or equal to p and qt is an accept state. Okay. So, there exists a sequence of states that the DFA takes, and such that the last state is an accept state and the number of states is 0 to t, which means t plus 1. Now, by pigeonhole principle, what can we say? So, how many states does the DFA have? So, the DFA has p states, and now we have a number t that is greater than or equal to p. Okay. So, therefore, in this sequence, actually in this sequence there are t plus 1 states because I start at 0, and t is greater than or equal to p, which means that by pigeonhole principle, there exists m comma n greater than or equal to 0 such that 0 less than or equal to m, strictly less than n, less than or equal to t. Okay. So, basically there exist and q of m equals q of n. Okay. So, in this sequence there exist two states which are the same, okay, two distinct states, okay, two states which are not the same, which are not in the same position in the sequence. So, they are at different positions, but the states are the same. So, there is a repetition. So, basically this is what we have. So, we are going from q0, there is some point where there is a loop, and from this loop we go to qt, okay, and this is the state qm or qn, whatever you want to call it. So, now what do we have? So, now we set basically x to be this portion of the string, okay, this portion from q0 to q. So, set x equal to the string from q0 to q m, okay, and let m be the first time there is such a repetition, which would mean that so this is x, set y to be this loop, okay, so the string on this loop, okay. So, y is the string on the loop and z is the remaining string. Okay. So, this means that, so if I do this setting, it means that the length of x plus the length of y is at most p, because the number of states is at most p, okay, and that is the first time I am getting a repetition. The length of y is strictly greater than 0, because this loop is non-trivial. There is some edge on this loop, okay, because of this pigeonhole principle that m and n are not equal, and z is the remaining part of the string. Now, basically the remaining part is easy, that for all I, if we look at the string x y to the power I z, it just means that after I take x, I repeat y I number of times. Okay, so every time I repeat y, I will end up at this state, and then if I follow z, I will end up at qt, which means that this belongs to the language error, which completes our proof. Okay. So, that will be all for today. Thank you.